In the last lecture, we discussed surface states, band bending, how the bands corresponding to the electronic states deviate as we move from the bulk to the surface, metal semiconductor interfaces, and Schottky and ohmic contacts. In this lecture, we will spend most of our time discussing semiconductor heterostructure, formation of the semiconductor heterostructure and the basic rules, how we align the bands corresponding to different semiconductors to form the heterostructure, and also the fabrication methods for lattice matched interfaces between two semiconductors. So the previous lecture, we discussed the interface between metal and semiconductor. In this lecture, we will discuss the interface between two semiconductors. So the relevant parameters for understanding how we can match two semiconductor surfaces and form a proper interface are the work function of the material. Work function is the energy required to remove an electron from the material into the vacuum, and electron affinity, that is the energy difference between the conduction band edge and the vacuum level, whereas work function is the energy difference between the vacuum level and the Fermi level. Band gap of these two material, the conduction band edge, valency band edge, Fermi level, that again depends upon doping and the built-in voltage. Okay. Now, in this picture, what we are seeing is two semiconductor, both are N-type. Both of the semiconductors are actually N-type semiconductor. We can see that because the Fermi level is close to the conduction band in both cases. Okay. And the vacuum level is somewhere here, and the band gap for this semiconductor on the left side, this is the band gap Eg1, and the right side you have the band gap Eg2, and here we have a situation where Eg1 is less than Eg2. That is what we have. And the guiding rule that tells how we are going to align two semiconducting material in the energy space to form an interface between two, to form a junction, that is called Anderson rule. So it's a very simple picture, but the realistic materials can be very complicated, and the rules also can be complicated, and it is involved. But this is how, to the first degree, that we understand how these two materials are joined. Okay. So the Anderson rule says that the first what you do is you align the vacuum levels, get the relative position of the band edges. So that is the first thing. So you have a vacuum level and you align the rest of the band edges, conduction band, valency band, and the Fermi level, everything with respect to that. So vacuum level is your reference. Vacuum level is somewhere here. So as you can see here, you have taken the vacuum level reference, and rest of them you can think as if you have actually hang from that point. Okay, it is hanging from that point, vacuum level. Then the band offsets at the interface that you can calculate using the electron affinities and the band gap. For example, the conduction band discontinuity at the interface, delta EC, that is basically the difference between two electron affinities, and the valency band discontinuity. In this case, you also need to consider the band gap differences too. Okay, so if you look at this, this is nothing but chi1 minus chi2, then you have Eg1 minus Eg2. That's what this is. So chi1 minus chi2, then Eg1 minus Eg2. You have to consider the difference of the two electron affinity and also the band gaps. Then only you can consider the discontinuity in the valency band. That is how you calculate. That much discontinuity you have to keep at the interface. Then you align the rest of the material such that the Fermi level at the interface is actually continuous. Fermi level throughout is continuous, because once you join these two material, the Fermi level, that's a level that tells the level up to which electron is filled. Until you join the material, the Fermi level can be different because the electron levels are different. Now, the moment you join these two material, the electron level should be same throughout, because it become now one solid. Okay, it's a one conducting solid. It's like you are taking two containers of water and you're connecting it with some kind of a tube, so that the moment you connect it, you're going to make the water level same in both containers. That is what you're doing here. Okay, so once you do all these things, you will get structure something similar to this here. So the band edge is here. This is delta EC, that is given by the two electron affinity. The delta EV, that is given by this thing here. Then you also made sure that the Fermi level is continuous here. Okay, for example, you can see that Fermi level is discontinuous in these two cases. Now you lowered it, but you have to keep that discontinuity at the band edge, both the conduction band and valency band, that need to be preserved there. Then you shift the rest of the bands so that the Fermi level is continuous. That is how you get this structure here. Alright, that is the process of aligning the bands to join two different semiconductors, or the same semiconductor but different doping levels. Alright, now let us look into what are the different cases of aligning these bands. So now what we have is, we have a material which is a combination of two different materials. So we call it actually heterostructure. Okay, so this is the case of an N heterostructure. I'm calling this NN because both sides are actually n-doped. All right. Now, depending upon how the band edges are going to align, there are basically three broad categories of heterostructures. All right. So the first one is type 1. We also call it straddling. So in this case, what you have is the conduction band and valency band of one side. This is the interface. Okay. This band gap in one material is larger than the other side, but they also align in such a way that the conduction band and valency band of the other material falls in the middle of this. Okay, so this is a straddling heterostructure. You have conduction band, valency band on one side here, other side here. It's like this. The second type is called type 2 or staggered heterostructure. Okay, staggered means again you have two different band gaps then, but when you do the alignment as prescribed by the Anderson's rule, you will do in such a way that this is going to be this way. Type 1 was like this will be like this. Okay, now this is called staggered heterostructure. Okay, and there is also a third kind, it's called mismatched or broken gap. So in this case, in the type 2 case, you still have a region where the band gaps are actually overlapping. Okay, here the band gap of the left side, right side is completely overlapping with that of the left side. In this case, there is a partial overlap, but in this case there is no overlap. The band gap in energy space is here, and the band gap of the second one is here. Absolutely, there is no overlap. That is type 3, or this is called mismatch. So in that case, what you have is you have structure, one of this material which forms the structure here, another one is somewhere here. Earlier, what we had is type 1, type 2, and this is type 3. This is called mismatch or staggered. Okay, and these are the three typical examples for each of these types. Okay, and the different quantities, parameters that you use to align these are given here, and this is your vacuum level, and this is also another way to illustrate these three alignments here. Okay, and the feature that we need to remember here is for type 1, the quantum well for the carriers in both bands. Quantum well for the carriers is there in both bands. Okay, that we will discuss that in detail, but what I'm trying to say here is, in the type 1 case, you can have a quantum well for both the holes and also for the electrons. Okay, and type 2, what you have is you have a quantum well in one and a barrier in other. So just to understand these statements, all you need to look at is these edges here. In this case, the well is going to form here because this is the lower energy for the electrons in this conduction band, and here you have holes in the valency band. A well is going to form here. That's in both cases. For a hole, this is the lower energy region, and for an electron, this is a lower energy region. Okay, so you have well for lower energy region for both holes and electrons. But in this type 2, what we are saying here is there is a well for one type of carrier, but there is a barrier for the other type of carrier. And it's easy to see from here, this is a well for this kind of carrier, but this is actually wherever it forms the well here, it will be a barrier for this carrier holes. But that is true for the converse is also true, because now there is a well here and a barrier here for the electrons if you for going by this way. Again, whether you will get a well or you will get a barrier or where the carriers end up, and all these depends on details of the doping and the other fine parameters of the interface, which is not a topic of discussion for this slide. But what I'm trying to say is broadly there are three kinds of heterostructure. There's a type 1, there's a type 2 and type 3, and they are classified according to how the conduction valency bands actually shifted in the energy direction in the energy axis with respect to the vacuum level. All right, so now let's take some examples. Okay, the most common example for a quantum well, or whenever we say quantum well, what comes to our mind is gallium arsenide, aluminum gallium arsenide material. Such a fantastic material, just given a lot of interesting and important results which are both thrilling for fundamental physicists and also for technologists. Okay, so the gallium arsenide system or gallium arsenide, aluminum gallium arsenide system belongs to type 1. Okay, so this actually, I would say this is type 1. So you can see that the aluminum gallium arsenide side has a larger band gap, the gallium arsenide has a slower band gap, and they are aligned this way. So this is a type 1. Okay, and here what we are seeing is an intrinsic gallium arsenide or undoped gallium arsenide where the Fermi level is lying in the middle, and the N-type or N-doped aluminum gallium arsenide. So the Fermi level is close to the conduction band. And of course, when you do the process, you had this structure initially. Now you have to, when you align the vacuum level, you got something like this. That's how you define the type 1, type 2, and type 3, how they are displaced when it is actually aligned from the vacuum level. Okay, this is type 1, and that is what we have for gallium arsenide. Now you have these two Fermi levels. So how these Fermi levels are aligned? So you have this Fermi level, and you going to shift it both sides so that Fermi levels are aligned. But that you have to do keeping the band discontinuity unaltered. So whatever the delta EC, these two regions you have to keep unaltered. Delta EC and delta EV, that you cannot change. But rest of things you have to align. Okay, when you do that, you are going to get a small triangle shaped well at the interface. Okay, this is the quantum well. Why it is a quantum well? We will come to that in a minute. Okay, this another example is indium arsenide, gallium, antimonide. Both are p-type, and that's what we have here. Here also, this is again, now this is actually, I would say this is like the type 3, because there is no much overlap between these two bands. Okay, so now you have to align in interface. You have to keep this way, but at the same time you have to align the rest. So you will get this quantum well in this case, and you can also get another quantum well, but that is in the other material. That's one quantum well is in this material, the other quantum well is in this material. But now, since it is a p-type material, so you have to consider that the holes are the majority charge carriers there. So you will have a quantum well in the valency band. In this case, you have a quantum well in the conduction band. Okay, so that is a difference. So here you have a hole gas. In this case, you have a electron gas. Okay, so you have a hole conducting charge carrier. Charge carriers are actually holes. Here, charge carriers are electrons, and we call them electron gas and hole gas. But that detail also you will see in either in this class or next class. But we call one as a hole gas because the point here is the electrons and holes in this material move like free electron gases, free electrons or free holes as the molecules of ideal gas. That's what we call hole gas or electron gas. But those details we will deal in a minute. Okay, in either in this class or next class we will do it. All right. So these are two different examples. One is a type 1 and this is actually a type 3. Okay, we have two kinds of systems here. All right. So now let us look at the common system, material systems, which generates all these different heterostructure. So this diagram here relates the lattice constant of various material and the band gap. So you will see very soon that the interface where these two materials are actually meeting is where all action is going to take place. As you have seen in the previous slide, your charge carriers are end up in this well, either here or here or here, which is right at the interface. So the quality of this interface is probably the most important thing when we consider these material systems, because that is where all the action, all the movement of charge carriers are going to take place. That is where these charge carriers are going to end up. Okay, so how good, how crystalline, how perfect this interface is of paramount importance. For that, what we need from the solid state physics point of view is a perfect lattice matching. When I say perfect lattice matching, is there are no defects or dislocations at the interface. We will address how these structures are grown, how these structures are made in the next slide. But this is going to summarize the importance and the quality of this heterostructure. So this axis is the lattice constant, and silicon is here, germanium is here, and the lattice constant of other semiconductors, 3,5s, gallium arsenide is somewhere here, gallium phosphate is here, aluminum, indium phosphate is here, indium phosphate is here, okay, and cadmium telluride is somewhere here, mercury telluride is here, indium antimonide is here, okay. Now, this two pictures here, these are TEM, transmission electron microscopy images of this interface. So you can see that there's a small color change here, and there is also a small color change here too, which is hard to notice, but here it is, in this specific it is apparent. So you have gallium arsenide phosphate and indium gallium arsenide here. So when you move from this region to this region, the interface is so perfect. You don't feel that there is any change. If you ignore that those are made of two different sets of material elements, if you just assume that those are all just points, lattice points, they're just continuous. There is not much mismatch between this system and the system. That means the lattice of these two materials are so identical that there is a perfect lattice match interface. Okay. Similarly here also, this is gallium arsenide, aluminum gallium arsenide interface. In this case also, you don't feel, as you draw a line from here to here, it's perfectly periodic. There are no defects, there are no dislocations. These are real images of these materials between these two systems. Okay, the perfect lattice match. That means the electron which moves through this interface is not going to feel any difference between that side and this side. Of course, it's going to see a difference in the energy of the two sides, the band gap in two sides, but there are no defects. It's perfectly periodic. Okay, and this graph here is showing you how the lattice constant is going to vary as you change the composition, because one side is you have gallium arsenide, so gallium arsenide, other side is aluminum arsenide. So you go from gallium and replace arsenide, and you go to aluminum gallium arsenide by replacing the gallium by aluminum progressively. So that is actually gallium 1 minus x, aluminum x. So you replace the gallium with aluminum slowly in this fraction. Now you can see how much the lattice constant is changing. So that is how these two materials are made. One is gallium arsenide, one is aluminum gallium arsenide. So if you look at the lattice constant here, this is gallium arsenide, aluminum gallium arsenide. They are pretty much almost on a straight line. You can see that. There's no huge difference between those two sides, right? So here also you can see that as you go from here to here, the lattice constant is changing by like a very, very small fraction, 5.653 Armstrong to 5.66. That is 0.01-ish approximately. That is the change. That is 1% change in lattice constant. I mean less than 1% change, right? So this is telling you how the various band edges are, or where the various band edges are, depending on the direction. For example, the band gap here is the gamma value. It's a direct band gap. Okay, when it's a direct band gap means the position where the minimum of the conduction band, maximum of the valency band, they are actually at the same k point, at the same wave vector. Okay, and this is gamma value. Okay, these details are not really relevant, but what I'm trying to say is this is telling you what is the typical band gap for this gallium arsenide. Now, as a function of the composition, this is how the band gap is going to change. I mean, band gap at various points are going to change. When you take, this is gallium arsenide, this is aluminum arsenide. So this is your compound where gallium aluminum arsenide, and X varies from 0 to 1. Okay. When you do that, you start from gallium arsenide and you become aluminum arsenide, and in between this is gallium aluminum arsenide. Now you can see that until a fraction of 0.4, close to 0.4, you can see that this gamma, or the direct band gap, this is the direct band gap. These are indirect band gaps. Okay, so this is the maximum of the conduction band. The maximum of the conduction band is not changing, but the maximum of the valency band is not changing, but the minimum of the conduction band is actually changing, right? So the band gap is actually from maximum of the valency band to the minimum of the conduction band. So this configuration for x is equal to 0, you have that at the gamma point. It's a direct band gap. But now, as you vary the x composition, you can see that the band gap is also increasing, because you have to go from here to here, right? This is the band gap. Gallium arsenide is here, aluminum gallium arsenide here. You need to go from here to here when you vary x0 to 1. What that means is your band gap is actually increasing. At some point of time around 0.4, now the band gap is actually above the x point, but x is actually an indirect band gap. Okay, that's the x value here. That's the indirect band gap. So what that means is the material is actually changing from direct band gap to indirect band gap. Okay, so for a lot of applications, we need direct band gap, especially when there are photons are involved, where optical transitions are involved. You actually need a material with a direct band gap. So almost all these devices are made with the composition X, which is less than 0.4. That's where most of these devices are actually made. Okay, that is kind of the overview of this gallium arsenide or 3,5 heterostructure, and how perfect, you can see how perfect those interfaces are, and you will see very soon that because of such a perfect lattice match interface, the electron also possesses really superior mobility and other transport characteristics. Now we can look into how these material systems are actually made, what process these material systems are actually made. Okay, there are two main processes where these really high quality, high purity materials are grown. They are stacked. The overall process is called epitaxy, where you are actually growing layer by layer, atom by atom of one material on top of the another material, and you can stack various materials in various sequences too. Of course, there are a lot of details, and this is a very tedious and very involved process which requires very expensive and highly sophisticated machineries and various characteristic tools and everything. And the first process is called molecular beam epitaxy, MBE. Here, it is very similar to it's a physical vapor deposition system where you have various pockets which are generally called effusion cells. You can think these are like some kind of container where the material that you want to deposit or you want to grow is there inside. That material is kept in that container, and you're going to heat it, and you will pass the vapors of this to certain substrate where you're going to grow this structure. And you have a lot of controls here. How many atoms are emitted, how many by controlling various parameters such as temperature, the pressure and everything. Okay. And this whole thing happens at really, really ultra high vacuum, something like close to 10 to the minus 11, okay, torr. Okay. Now there are various characterization tools such as read or XRD, OJ spectroscopy, all kinds of thing which is going to verify that you are growing the right material and right sequence and everything. All this characterization happens in situ. Okay, and a lot of other bells and whistles to this. Anyway, but this is just an overview, and this whole thing is called MBE or molecular beam epitaxy, and this is a picture which we have seen in the previous view graph where you have interface of gallium arsenide and aluminum gallium arsenide which are grown in sequence and like a grating. Okay, and as you can see, as you go from one end to the other end, you don't see any change in the periodicity of the overall lattice because they are so close. The lattice constant of these two material, aluminum gallium arsenide and gallium arsenide, are so close that doesn't change very much. Okay, this is one technique, and the other technique is something called MOCVD, that is called metal organic chemical vapor deposition. Okay, here this is a CVD process, chemical vapor deposition process, but this is also involved. But it's a reactive process where you have the organic compound, volatile organic compounds of the species that you want to deposit. In this case, the illustration here is you are depositing an indium phosphate. So what you have is indium and phosphorus layers. But there are two kinds of reactive gases here. One is trimethyl indium, and you have phosphine, pH3. So these two you will pass into some kind of chamber. Of course, a lot of calculations and a lot of simulations are done to design this chamber and what direction, how you pass it, pumping speed, all kinds of things are actually involved. Then you have a substrate holder where it is hot, everything is kept hot, and the gases will hit the substrate where you are keeping all these wafers, which you can see the circular thing which is on that hot surface. Then when it will hit, it will undergo some chemical reaction, is going to get adsorbed these different species, and there are some pumping mechanism which will pump out the other volatile part, in this case the CH4 with the byproduct that will leave the chamber, and you will end up with getting only the required on the elements, that is in this case indium and phosphorus. So of course this is also a very popular process, especially for industrial scale growth, because MBE, what we discussed in the previous slide, is a very slow process, and it takes a lot of time, and there are uniformity issues because all kinds of things are there. But for a commercial scale fabrication of heterostructure, for example, for applications in light emitting diodes or all kinds of other optoelectronics application, where for example your screen, computer screen, all kinds of things, those are all made by CVD, okay, or MOCVD process, because you can grow large area heterostructure with a relatively very good uniformity. And one important thing that I would like to notice, or I would like to bring it to your notice here, is the MBE is actually a high vacuum process. Okay. I would say ultra high vacuum process, whereas this is actually a low vacuum process because it's a CVD process. You have gases flowing into the chamber. Low vacuum. It's a low vacuum process. Okay. And there are these organic compounds corresponding to whatever elements that you want to deposit. There are always some kind of organic compounds available. For example, silicon is grown by using something called tetramethyl silane. It's a liquid, okay, and you will heat it and you will get the vapor. And gallium is grown by trimethyl gallium. Germanium is grown by tetraethyl germane. So you will find, I mean, this is just a few examples. You will find the corresponding metal organic compounds for all the commonly used material to grow this, and this is a very, very popular technology. Okay, so this is how these are the two techniques how the epitaxial growth of these heterostructures are actually grown. So in the next class, what we will do is we look into the details of these interfaces that has been created by combining two semiconductors. All right.